So today we have discussed about evaluation of constant in the Maxwell Boltzmann distribution law. First, we have discussed about the postulates of Maxwell Boltzmann distribution law. The assemblies consist of three general kinds of particles. So first one, identical and indistinguishable particles of any spin. Second one, identical and indistinguishable particles of zero or integral spin. Third one, identical and indistinguishable particles of half spin. So next, Maxwell Boltzmann distribution law. So first we consider a system of n similar but distinguishable molecules of gases. So already we know that the instantaneous state of a molecule, which is represented by the phase space in that particular space. So let the space is divided into a large number of cells. So consist of 1, 2, 3 to up to ikn. Okay, so in that cells, the number of particles which can be expressed in n1, n2 up to nk. So in the first cell, we having a particles n1. In the second cell, n2, and similarly for the third cell, n3. So up to nk. So the number of gases whose space points lie in the cells 1, 2, 3 up to k respectively in the equilibrium state. As the gas molecules are moving continuously, so Ni state will change continuously in many different ways. So here the most probable state which can be expressed in the form of Ni, which is equal to Agi e power minus beta Ei. So where A which is equal to e power minus alpha which is equal to constant. This results determined the most probable distribution of the molecules among the various possible individual states and is known as a Maxwell Boltzmann distribution law. Here Ne represents the number of molecules having energies between E and E plus dE. So if rho is the molecular momentum, then E equal to P by 2m. So equation 1 which is written in the form of N of P dP which is equal to Ag of Pe. In E itself has infinite volume H, then Gp of dP which is equal to triple integral of ds, that means surface integral dx dy dz dpx dpy dpz by h cross. If the volume V is occupied by the gases in the ordinary position state, then surface integral of dx dy dz which is equal to B. So for the volume between the two spheres of radii P and P plus dP will contain all the molecules in the momentum having momenta between P and P plus dP. The volume between two spheres is given by volume integral of dpx dpy dpz which is equal to 4 by 3 pi P plus dP the whole cube minus 4 by 3 pi of P whole cube which is equal to 4 pi P square dP. Substituting the values from equation 4 and 3 into, we get Gp of dP which is equal to V 4 pi P square dP h cube. So the final equation, since for the total number of molecules which is considered as n, that is integral of up to np dp which is equal to n. So the integral of equation 6 which yields the equation n equal to v 4 pi a by h cube integral of 0 to infinity p square e power minus beta p square by 2m into dp. So here the standard definite integral of 0 to infinity x square e power minus alpha x square dx which is equal to 1 by 4 square root of pi by a cube. So substituting the value of substituting the value of integral in 9, we get a which is equal to n h cube by v beta 2 pi m the whole power 3 by 2. So the total energy in that particular system is given by E which is equal to 3n by 2 beta. Here we consider the non-interacting gas molecules according to the kinetic theory of gases. The total energy E and n when the number of molecules of an ideal gas at the absolute temperature T which is equal to E equal to 3 by 2 nkt, where K is a Boltzmann constant which is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. So beta which is equal to 1 by kt. So the Maxwell Boltzmann constant C which is equal to 1 by 2 pi mkt whole power 3 by 2 into B. Okay, thank you girls.